Okay, let's dive into this. Welcome to today's Explainer, where we're going to completely deconstruct the incredible, roaring machines that make modern global travel possible, the jet engine. If you've ever found yourself looking out a terminal window, just kind of wondering exactly what is happening inside those massive metal pods hanging under the wings, well, you are definitely in the right place.
First things first, we've got to bust a really common myth. When you hear the term jet propulsion, it is so incredibly easy to picture a giant, chaotic, continuous explosion happening inside that engine casing. But honestly, that is entirely wrong. A jet engine actually operates a lot more like a super powerful, highly engineered fan. So instead of a bunch of crazy explosions, it relies on a remarkably stable, carefully controlled, high-speed flow of hot gas.
So the crucial point is that to truly grasp how this all works, we just need to look at a fundamental rule of physics you probably learned way back in grade school, Newton's third law. It states that for every action, there's an equal and opposite reaction. And this simple, elegant rule, it's the absolute foundation of all jet propulsion. To bring this physics concept down to earth, I absolutely love this analogy from the engineers over at Rolls-Royce. Imagine for a second you're standing on a skateboard, and you're holding a heavy-duty fire extinguisher. If you open that extinguisher, it shoots a highly pressurized stream of gas forward. And what happens to you? You get pushed backward. Well, a jet engine works precisely the same way. By forcing an immense amount of air out the back, it pushes the entire multi-ton airplane forward.
Here is a quick roadmap for this explainer. 1. Busting the myth. 2. Suck, squeeze, burn, blow. 3. Waking up the beast. 4. Conquering extreme weather. 5. Jets versus piston engines. And 6. The future of flight.
Let's get right into the mechanics with Section 2. Suck, squeeze, burn, blow. Aviation professionals actually use this very famous, catchy little mnemonic to remember exactly how a turbine works.
Think about a perfectly orchestrated symphony, or even the script for this very explainer. For it to work, you can't just have random notes or thoughts thrown together, right? It requires a seamless transition from one idea to the next. A jet engine is exactly the same way. It doesn't run on individual, stuttering explosions. It requires a perfectly orchestrated, continuous, unbroken flow of air all the way from the front to the back.
And this brings us right to those 4 steps: suck, squeeze, burn, and blow. First up is intake. The massive fan at the front, like the single-stage fan you'd see on a regional jet, draws air in. Now, a lot of this air actually bypasses the core entirely for thrust and cooling. Second is compression. The air that does enter the core gets violently squeezed by rows and rows of compressor blades, up to 14 stages in some jets. Third, combustion. That highly compressed, incredibly hot air mixes with fuel and burns continuously. And finally, exhaust. That expanding, fiery gas blows right out the back, spinning the turbine blades that keep the whole cycle running.
Which naturally brings us to Section 3, waking up the beast. Because knowing how it runs is one thing, but how on earth do you even start a machine this massive? I can assure you, you absolutely cannot just step outside and hand-prop a commercial turbofan like an old biplane.
Think about the sheer scale of the physics happening here. During a start sequence, the engine's core, which is known as N2, has to be spun up to 14% of its maximum speed. That is 2,200 RPMs just to get the igniters to fire. From there, it has to accelerate to 28.5% N2, which is over 4,500 RPM, just so the engine can safely introduce fuel. And when it finally does, it's dumping fuel at a rate of 200 pounds an hour. To put that in perspective, that's about a half gallon every single minute.
Now, what's really interesting about this is how they get that massive initial spin. You need extreme air pressure for that. Normally, this comes from the APU, which is a small auxiliary turbine hidden back in the tail. But if that's broken, ground crews hook up what's called a huffer cart, basically a massive external air compressor. Or if one engine is already running, pilots can do a crossbleed start. That means they steal compressed air from the live engine to wake up the sleeping one. Pretty clever, right?
Moving on to Section 4, conquering extreme weather. Because once these beasts are awake and up in the air, they certainly don't get to operate in perfect laboratory conditions. They have to keep hundreds of passengers completely safe, even when Mother Nature gets utterly chaotic.
So when you're flying through a massive, heavy rainstorm, you might wonder, can a jet engine flood? Well, the answer is no. These engines are rigorously tested and certified to withstand ingesting up to 4.5 tons of water every single minute. Let that sink in for a second. That is an astonishing volume of water rushing through a highly complex machine without stopping it.
How does it even survive that?
Well, the engine actually defends itself naturally. Those spinning fan blades create a huge centrifugal force that literally flings most of the rain outward, completely bypassing the core. Any water that does make it inside gets instantly evaporated by the extreme heat of that compressed air. But here's why this matters for safety. While water is totally fine, ice and hail are absolutely not. Ice buildup ruins aerodynamic efficiency, which is exactly why jets have to use specialized heated anti-icing systems. And hail, chunks of solid ice can physically crack those delicate internal blades. That's why pilots navigate strictly around thunderstorms.
Let's move to Section 5 and see how this builds into the bigger picture: jets versus piston engines. Let's look at the broader landscape of aviation to see exactly why we rely on jets instead of the piston engines that dominated early flight.
Ultimately, it all comes down to reliability and safety. If you look at a standard piston engine, say on a Cessna 172, it requires a complete teardown overhaul every 2,000 flight hours. But a commercial jet engine? It easily pushes past 10,000 hours between overhauls. Because there's no harsh up and down reciprocating motion, just that continuous rotary flow we talked about, commercial air travel is incredibly, undeniably reliable.
In fact, jets boast 7 core benefits over pistons. They produce way less vibration, they have those huge overhaul times we just mentioned, and they don't suffer from propeller stall limits. Plus, they have this amazing feature called ram recovery. Essentially, once you hit 60 knots, the sheer speed forces so much air into the engine that it acts like a natural turbocharger. This allows jets to fly at much higher altitudes, climbing right over the weather while producing massive power per pound of weight. And for the pilots up front, the controls are incredibly simple. You just manage the thrust levers and let the computers handle the rest. Which leads us to our final topic, Section 6, the future of flight. We have these highly reliable, incredibly powerful machines today, but the aerospace industry is actually facing its biggest evolutionary shift since the invention of the jet itself.
From an economic standpoint, the growth we are seeing is just staggering. In 2023 alone, manufacturers produced over 9,200 new engines just to keep up with the worldwide demand to modernize fleets. The market is projected to rocket from roughly $153 billion today to nearly $280 billion by 2022. The demand for flight is, quite simply, insatiable.
But here is the ecological reality we have to face, and this brilliantly illustrates the challenge ahead. While 600 million liters of sustainable aviation fuel, or SAF, were produced in 2023, and Airbus even successfully flew a test flight using 100% unblended SAF, which is amazing, it still accounts for a mere 0.2% of global jet fuel use. The vast majority is still traditional emission-heavy jet fuel.
Which leaves us with the ultimate question for the next generation of aerospace engineers. We know the physics of jet propulsion are sound, the safety is unparalleled, and the market is booming. But with the rapid advancement of engine technology and the urgent push for sustainable aviation fuel, how quickly can we truly green the skies? Definitely something to think about next time you look out the window at 30,000 feet. Thanks so much for joining me on this explainer, and keep your curiosity flying high.